Okay, let's dive right in. We're going to unravel one of the coolest ideas in physics, the structure of the atom. And to get our heads around it, we're not going to think of a tiny solar system. Instead, let's imagine the atom is a skyscraper, and its electrons are riding a very, very special kind of elevator.
You know, this whole thing started with a simple question that was a huge mystery about a century ago. When you heat something up, why does it glow with a specific color? Why isn't it all just a generic white light? Scientists noticed that every element, when it got zapped with energy, gave off its own unique set of colors, like a kind of atomic fingerprint.
And the answer to this colorful puzzle? Well, it didn't just explain the glow, it completely turned our understanding of energy and matter on its head. This was a massive turning point for science. Yeah, the old physics rulebook, what we call classical physics, it was failing. Its models treated light like a smooth, continuous wave, and they just had no way to explain these distinct color signatures. Something was fundamentally off with how we are looking at the universe. The big aha moment came from a totally radical new way of thinking about energy itself, and it wasn't really about waves or particles, not at first. Believe it or not, it was about stairs. So, we used to imagine energy like a smooth ramp. Makes sense, right? If you're walking up, you can stop at any point. Your energy could be a 1 or maybe 1.1 or 1.11. Literally any value is possible. It's totally continuous. That's the intuitive way to think about it. But what if energy isn't a ramp at all? What if it's a staircase? You can stand on step 1 or step 2 or step 3, but you can't just hover in between the steps. A physicist named Max Planck came along and said that energy works just like this. It comes in distinct, specific packets. He said it was quantized. And the name for these little energy packets is quanta. A single one is a quantum. This idea is the key that unlocks everything else. Energy isn't a continuous flow, you see. It's a series of individual steps. So what on earth does this have to do with atoms? Well, a brilliant physicist named Niels Bohr took Planck's staircase idea and applied it directly to the atom. And this is where our skyscraper analogy really comes to life. So picture this. The atom's nucleus is the solid foundation right on the ground. And the electrons? They aren't just buzzing around randomly. They're like residents who can only live on specific, predetermined floors of this skyscraper. Now, in physics, there's a term for the lowest possible energy level for an electron. We call it the ground state. It's where everything is stable and settled. And in our skyscraper, the ground state is just the lobby. It's the first floor. It takes the least amount of energy to be there, and it's the electron's default, most comfortable home. So the opposite of the ground state is what we call an excited state. And that's just any state where the atom has soaked up some extra energy and has more than it does in its ground state. Back in our building, an excited state is simply any floor above the lobby, the second floor, the 10th, maybe even the penthouse. And just like in a real building, an electron can't just magically appear on a higher floor. It needs a boost of energy to get there. So how do these little electron residents travel between floors? Well, they take the electron elevator, and this is how we're finally going to solve the mystery of that colorful glow. Okay, so check this out. This diagram, it's basically the architect's blueprint for our atomic skyscraper. Each of these lines, n equals 1, n equals 2, and so on, that's an allowed floor, an energy level. And just like with the staircase, an electron can exist on one of these lines, but it can never, ever be found in the empty space between them. All right, so the elevator ride goes like this. First, an electron is just chilling in the lobby, the ground state. Then it absorbs a specific packet, a quantum, of energy. That energy is just right to send it instantly, and I mean instantly, up to a higher floor. Let's say the third floor, an excited state. But it's unstable up there. It can't stay for long. So what does it do? It falls back down. And as it falls, it has to release all that extra energy it absorbed. It does this by spitting out a photon, a tiny particle of light. And this is it. This is the solution to our mystery. The color of that little light particle depends entirely on how many floors the electron falls. A big drop, say from the 5th floor all the way back to the 1st, releases a lot of energy, and that gives you a high-energy blue or violet light. But a small drop, maybe just from the 2nd floor to the 1st, that releases way less energy, and that's a lower-energy red light. Every element has a unique set of floors, so each one has a unique set of colors it can emit. This whole concept, this entire atomic skyscraper, that was Niels Bohr's model.
And it was an absolutely brilliant blueprint that finally connected the new idea of quantized energy with the structure of the atom. So, what did Bohr's blueprint give us that we still use today? Well, first, the huge idea that electrons live on these specific floors, these discrete energy levels. Second, that atoms only absorb or spit out light when an electron jumps between those floors. And maybe most importantly, his model finally explained why atoms are stable. It showed that when an electron is on an allowed floor, it doesn't just radiate away energy and spiral into the nucleus, which was a massive puzzle for the older models. Now, it wasn't perfect. Of course not. The model's math worked beautifully for simple atoms like hydrogen, which only has one electron. But as soon as you got to more complex atoms with more resonance in the skyscraper, the model, well, it started to break down. It was a vital first step, but it wasn't the final picture.
So what's the big takeaway from all this? Bohr's model was a monumental leap. It gave us the blueprints for the skyscraper, correctly identifying all the allowed floors. But it left us with an even deeper and frankly weirder question. What exactly is an electron doing when it jumps between floors? And what does the space between them really look like? Answering that, well, that would take us into the even stranger world of quantum mechanics.